Okay, so hello everyone. I wanted to ask first, do you have any questions from the last time? Uh, so, or shall I just start? Uh, yes. So today I'm going to tell about a more complicated green function, namely about the green function of the wave equation. Namely, we want to solve the following equation: d over dt to dt star minus d over dx1 squared minus and so on minus d over dx n squared. Oh, wait, I used d u equals to f. So uh, the question is, what is u? How to write at least some solution of this equation? And this t comma x1 xd will write for simplicity in r d plus 1. So it's just whole space without boundaries. Because in this case it is easy to find this green function using Fourier transform. So as we remember, we can d2. As I remember, we can, and this is called the number operator. It's denoted by box. So in principle, we would like to solve an equation for the green function. The number of g equals to delta function of t, a delta function of x. And if you do the same as we did for the Laplace operator, we can say that this equation for Fourier transform green function is like minus k0 squared plus k1 squared plus and so on plus kd squared times g tilde equals to 1. So it means that this g tilde, so it's our problem, this g tilde is equal to 1 over minus k0 squared plus k squared. And it is a problem because we remember that even in the in that case Laplace operator where all the signs were pluses, it was not a in L1 it had a singularity at 0, but here the problem is that singularity that this singularity lies on this huge hypersurface k0 squared plus k squared equals to 0, and it's namely, it's unclear how to take inverse Fourier transform of this function, because we will have some divergent integral. So mm, so what shall we do here? Um, so the origin of this singularity is quite clear, because you see there is this operator, and if we act on a simple exponential, e to by the way, I'm using this notation. K0 is the same as omega, like the same as omega, t and the same as x0. So it's just a different notation for the same letter. So the origin of this singularity is that this equation has a huge number of solutions, which are they are not in L2, for example, then also not integrable, but they somehow behave as constants, and the solutions are e to absolute value of k t minus plus I k x. There are plane waves which solve this equation, and this is so it equals to 0. So this is of course what we expect. That the wave equation describes plane waves which propagate with speed 1 in the direction given by k over absolute value of k. So this exponential is so this minus t absolute value of k. So if k is, for example, 1, 0, 0, 0, and then it is e to minus I k1 t minus x1. So it's clear that it is some plane wave, a function of only the difference of time and a coordinate. So it propagates this on this unit speed. So and the question is what to do with this gain function, and as before, let us first look at the case d equals to 0. So this gain function is g tilde is 1 over minus 1 over k0 squared. Actually, I was cheating the last time because I wrote a general formula for the inverse Fourier transform of this gain function in the arbitrary dimension. Then I substituted d equals to 1. But I neglected the fact that in that case this integral is actually divergent because it's 1 over k square at k equals k equals to 0. Uh, so. But maybe it's actually better to use not k0 but omega squared. Maybe I'll do this because there are integrals in this omega. Yeah. So uh, the question is how to take the inverse Fourier transform. And remember this consideration of the wave equation in the uh, in the rectangle. That in that case, it is always problematic if we try to give boundary condition for this problem. So we should look for some solution of a problem with fixed initial conditions, which means that this gain function should depend only on the this gain function tx should depend only on the values of the right hand side in the past, which means that this gain function should vanish for t less than 0. So we ask for this. And this means the following. So we need to compute the Fourier transform of this G tilde. But it has pole at 0. Mm. So, hmm?
If we don't set G to be 0 or t less than 0, we get anyway another wave function, and then we have to adjust the solution of the homogeneous equation, or we don't get anything.
This gain function is not defined because if we just write the inverse Fourier transform of it, the integral will be divergent. So we can define it in several different ways. We will actually look at these different ways, and they will give different answers. So here, so there is the second order pole in the omega plane. So we remember that if we compute this integral g of t it is an integral like from minus infinity to plus infinity e to e minus e to minus I omega t dt over omega squared. So if we ask that it is 0 for negative values of t, it means that we should be able to close the contour in the yes, thank you. Yeah. Mm. So if we have if we ask it to vanish for negative t, it means that in this case we should be able to close the contour in the upper half plane and don't meet any singularities. So it means that so uh, this contour, like so when t is less than 0, we can do this, and so it's when oh, no, maybe I should draw this picture in some other place. So when t is greater than 0, when t is less than 0, then this contour can be closed in this way. When t is greater than 0, it can be closed in this way. This is omega plane. And we know that this should vanish because we asked for this. We are looking for such increment function. So idea is very simple. This second order pole should be moved a little bit under the real line. So it should be here, which means that this integral should be modified by adding here plus I epsilon. And if you now compute what it gives, this gives just 0. Sorry, I also forget a factor 2 pi for the Fourier transform. So here it is just 0, and here we need so it goes counterclockwise around this pole, so we should take a minus derivative of this exponential and then multiply it by 2 pi I. So derivative gives t, and the answer is that it is t. So if you combine these two formulas together, and we get that this green function equals to t heaviside theta of t. So here's the train.
If we leave the pole where it is at the beginning and we consider the principal value, we can still make the computation.
Yes, let us do this. So we will also see the known result. So some G1, for example, of t is a principal value of this integral. Uh, Actually, mm, I'm not sure that it works for this singularity. Let me think. Because if there is if there is first order proof, we can just say that a principal value by definition. Uh, so um, if there is first order proof, then it works like this: principal value of integral from uh, like from a to b minus a to b, f of t over t dt is by definition a limit when epsilon goes to 0, uh, integral from minus a to minus epsilon minus integral from plus integral from epsilon to b f of t over t dt, and this limit exists because the behavior of 1 over t is this one. And this is 1 over t. So this integral, so these contributions for positive and negative t cancel. But and we can also notice that this integral is 1/2 of the integral in the complex plane, 1/2 of how to, maybe I will just draw two integration contours here, like this integration contour plus this one. Right? F of t over t dt. So is this notation clear? So it's integral over this contour plus integral over this contour. But if we now try to define a principal value of some higher powers of t, then we don't have this intermediate definition anymore, for example, for t squared, because t squared is positive both for positive and negative t, so this integral will still be a divergent, it does not have a limit. So the principal value of the integral of like to be f of t over t squared dt can be defined only as this half half sum of the contours. This integral
depends also on f, I imagine, because if, for example, f is odd or even, we can have convergence also on that term, or
No, if f is even, or if f is odd, it is a kind of cheap trick because it behaves like 1 over t, and we are still in this situation. But here we have a f which is neither even nor odd. It equals to 1, and it has some derivative in 0. So mm,
so the competition is just a way of finding a candidate to be a green function, but not in principle a green function itself, since we are not integrating over omega squared, so we don't have the reverse Fourier transform of. So we have to check that the function we got is a green function.
no. Why? So if compute a convolution of this gain function with the right hand side and act with D'Alembert operator, we see that the answer has a limit when epsilon goes to 0, and this answer is well, because convolution is just multiplication of the Fourier images. So we see that we recover the right hand side, like uh, like u tilde equals to f tilde over like minus f tilde over 2 pi omega minus I omega plus I epsilon squared. Like here I suppose that we are epsilon is infinitely small, so we are taking the limit. Uh, and then the Lambert of U Fourier transformed is uh, so I don't know. No, I shouldn't have written this to pi here because it's in the Fourier transform. So if you act with the Lambert operator, we get omega squared over omega plus I epsilon squared times uh, f tilde. And when epsilon goes to 0, it goes to f tilde. So in this way, we prove that this is actually a solution of our equation. The only question is which precise solution we get in this way. Because this operator has a kernel. There are functions, for example, in this case, there are exponentials. In this case, they are a constant linear function. So different gain functions can differ by addition of this solution to the homogeneous equation. And this particular function gives a particular solution.
Okay, so it's just a clever choice to get to the initial conditions only once.
Uh, so
So initial homogeneous conditions, probably.
no, the point is that this um, uh, so how to say it, so if I imagine that f of x and t is uh, if t equals to 0 when t is less than uh, some minus t, for example, uh, then our solution u of t and x equals to 0 for t less than minus t. It means that the waves in the solution of this wave equation are generated only by the right-hand side. They did not exist before we applied this external force. So probably I should draw some picture, but
doesn't appear in the integral
hmm?
because we also implicitly taken the limit.
Yes, of course. It goes to 0, and we can just say that it's not. We can say that we are not shifting this epsilon, but this omega, but we put so when epsilon goes to 0. We can say that we just deform this contour. So this contour goes like this. In this case, and yeah, and in the same and behaves in the same way here because it's the same contour.
Yeah, but written in this way, it seems to me that also the first should not be 0 because it is affected by the pole.
No, there are no singularities on this contour, so we can just pull it up. So there is a contour which does not have any singularities. It goes close to the singularity, but it's outside.
But even if it is outside, when you restrict the circle around the pole, you get the half value of the decision. Yes, since the integral on the half circle does not go to 0.
No, but but it means precisely that this integral over the half circle equals to minus everything else. And, for example, there is this computation of the example. Do you know the value of this integral? Hmm. So does anyone know the value of this integral? Hmm? So, no. It's very close, but not that one. So let us actually compute it. So we can first say that this integral is uh, is oh, it's integral from minus infinity to minus epsilon plus integral from epsilon to plus infinity sine of x over x dx. In the first step, it's an innocent procedure because this function is defined at 0. Then let us say that this function is let us say that if we now take cosine of x over x times dx, it will be an odd function, and this integral will vanish. So we can say that it is integral from minus infinity to epsilon plus integral from epsilon to plus infinity e to the ix over x dx, because cosine part will vanish. Do you agree? And then at this moment we have this precise picture. So we have integral from over this line to minus epsilon to plus epsilon to infinity. So we are missing this one part of the integral. And we know that in principle we can close it above. We can close this integral here. So this part will be 0. But it's not closed around it's not closed around 0, and we can say that we are closing it like this. No, not like this. Or maybe we will close it like this. It will be integral. It will be c. So so this integral will equal.
Shouldn't it divide also by I the integral? Because e to the I
Yeah.
I is an x.
Well, let us just write that it is an imaginary part of it. And no, let us put 1 over I in the denominator. So let's actually call this part c epsilon on this integral. This piece c0 and this c infinity. So our integral is over c epsilon, but let us write it this way. We can say that it is integral over c epsilon plus c 0 plus c infinity e to the ix over ix dx. But originally we had only this contour, so we should subtract two other integrals: integral over c infinity and integral over c epsilon, the same function. So now the question: what is the value of this integral? Yes. So this one is 0. What is the value of this integral? Uh, Actually, it's in the clockwise direction. Uh, yes. So it equals to pi. All right. And what is the value of this integral? So, sorry, this is minus pi because so and there will be extra minus. Yes. So, well, so if we try to say that we should somehow take into account this pole, which is at the boundary of this contour, then we'll get something strange, like the original integral is 0. But you see, so the answer here is pi. But you see, it does not matter what happens at the boundary of the contour. You can still deform it whatever you want.
Yeah,
Like,
the reason why we get pi is exactly because we have a point zero, which is not in the interior of the contour, but still.
no, it was not on the contour at all. Our contour was not closed originally in this computation. So we had to close this contour to get to add this extra contribution. And after this, we can say that this integral is 0, and we are left only with this part. But here we had the closed contour from the very beginning, because it's just the definition of the Fourier transform. So we first try to integrate over the real line, then with this shifted pole, and then we perform. Then we take a limit at the level of the integral. We deform this contour a little bit because deformation does not change the answer. If you don't close any singularities. And then we move this pole back to its position, to 0. So,
we decided to integrate it that way because we need that the green function is 0 behind the.
yes, precisely.
So if we needed for some reason to have that condition equal to 0 for t bigger than 0, we would have integrated on the other.
Yes, of course. And this is and if you take 1/2 of some of such integrals, we will recover precisely this definition of the principal value, which we wanted from the beginning. And on the right hand side, it will correspond to this 1/2 of the absolute value of t, which we obtained the last time. So.
So the last integral is over C0, right?
Oh, sorry. Yes. Thank you. Yes.
I still don't get why that integral should be 0, but.
Which one? This one?
Yeah, I agree that if we leave the pole there, we get 1/2 self-adjoint function.
No, 1/2 of the absolute value of t is obtained by a superposition of such integral and the integral. Let me write a formula. So if you take integral over this contour, right? What was there? On this one. Maybe minus. So this will equal to what? This will equal to 1/2 of theta heavy side theta of t minus t heavy side theta of minus t. So it is 1/2 of the absolute value of t. And it does not equal to the integral from minus infinity to epsilon plus to minus epsilon to integral from epsilon to plus infinity. To minus I omega t. And because this limit does not exist. So is it fine? Oh, but again, concerning this integral, originally we had this picture, and this is for t is less than 0. Originally we had this picture. Pole was here. Then, if we want to play with poles of a function and we want the integral to be continuous, we should care about integration contours. It means that poles should not cross these contours, because any crossing means a jump of the function. But we can avoid this, for example, by deforming this contour in advance. We can say that it equals to the integral over some contour like this. So it's just the same, because it's a holomorphic function. So we can move this contour somewhere else, move it up, and then when epsilon goes to 0, it can be deformed to something like this. So this pole is here, and this contour is somewhere else. So it does not contain singularities. It goes to 0 at infinity, so it's clearly 0. It can be shrinked. But we can also, so all this is 0, but we can also put this controller back to the real line and draw something like this. You can choose some very big circle around 0. And then close this control somewhere else. But it's still 0 because it does not have singularities inside.
Okay, but
And
how can we relate with our integral that goes from minus infinity to plus infinity?
oh, but we just so our integral, which goes from minus infinity to plus infinity, should be defined somehow. So we either define this control from the very beginning, or we can say that we first shift this pole a little bit below the real line, and then we can take a limit epsilon goes to 0 at the level of this integrals. So we should not so how to say it. Mm.
So take this limit of this integral with the pole away from 0, but then we have to check that that is a green function.
No, because because we can think in terms of mm, let me think. Oh, so one argument is that we can perform this speculation with the modified gain function and say that its limit epsilon goes to 0 recovers original function. But another argument is that we can try to modify this contour in this way in all possible Fourier transformations, I think. So. Mm.
Can I ask you one last thing about
Yeah.
this, just to know if I understood what we have done? So in general, we have an integral that has a principal value that is not well defined. So
no, it has principal. It has kind of a stupid principal value, which is not well defined. If we just try to take a limit from both sides and integrate, then it is a ill-defined procedure. This limit does not exist. But there is a clever definition of the principal value for higher order poles. We just take 1/2 of the integral with such over such contour and over such contour. So in this simple case, it coincides with the usual limit, but here it is something else. So is it fine? Actually, we can check what is the difference between this integral and this naive limit, because let us try to compute the integral over this. Let us call it this C plus integral over C plus, or f of t over t squared dt. It is integral of so the only relevant parts are f of 0 over t squared mm, squared plus f prime of 0 over t dt, and it equals to f of 0 over it equals to pi. So it equals to f of 0 minus f of 0 over t from minus epsilon to epsilon minus pi I f prime of 0. And if you compute the same integral for C plus, for C minus, so here it's the same, and here it is plus pi I f prime of 0. So some of them equals to we should take this twice and so if it, yeah, so and it gives 4 f of 0 over epsilon squared, and this part cancels. So we see that contribution of this small integrals over epsilon, sorry, and give something non-trivial. So we should not just take this limit, we should also subtract this 2f of 0 over epsilon, and well, in principle, it is doable, but it is much easier to say that we just take um, half half sum of this two contra integrals.
We start with the integral that does not converge, and the idea is to assign a value to this integral, even if it does not converge. Right?
Now, the idea is to define some other integral which converges and
without the epsilon does not converge. Am I right?
yes, of course.
So we try to assign a value, and one possible way is to extend the definition of the principal value with the path procedure.
Yes, it's one possible way, but it's not the best one. Because the interesting gain function corresponds not to this principal value, but to such contour, because it corresponds to correct initial conditions, like that it's initial condition, not boundary condition, and it corresponds to such solution. So
this is not it is not equivalent to this one when we so what I want to say is that the moving the critical point the pole does not correspond to change the path or the two procedures they correspond.
what do you mean?
I mean, considering the singularity fixed and changing the path, and the second procedure, moving the singularity and maintain the path the same, the two procedures corresponds or they give two different values?
You mean if we first move pole here and then compute the function, or we consider this control from the beginning, if they equal or not? Isn't the question?
The previous, the omega plus the epsilon, and the other is this one here where we leave 1 over omega squared and change the path.
They are equivalent in the limit because once again we define let us define g epsilon which is integral from minus infinity to plus infinity mm, d omega over 2 pi minus e to minus I omega t over so g epsilon of t over omega plus I epsilon squared. Uh, mm, uh, mm, there is, I don't know if you can call this theorem, but a statement that a limit when epsilon goes to 0 uh, uh, of this function g epsilon of t exists. This exists and equals to this integral. To integral over this contour. And a proof of this, yeah, and we can call on this limit g of t. A proof of this statement is very simple, because here we have an integral of the analytic function, and this integral equals like for any epsilon, this integral equals to this integral. For example, let us say that it is a unit circle, and if we do if we do this, then then our integrand, this omega plus I epsilon, like so. Let us compute the difference. G epsilon of omega minus g minus g of omega. It equals to 1 over omega plus I epsilon squared minus 1 over omega squared. So this equals
The second one, limit epsilon goes to zero of the epsilon equal to the integral of this with this path, and the path is from minus epsilon to plus epsilon.
no. It's a limit from for epsilon goes to 0, and the right hand side does not depend on epsilon. Uh, so So integral of the analytic function does not depend on integration path if we don't cross singularities. So it's constant under continuous deformations of the integration path. So it's just a topological property. That, so it is 0. So, and here we are using the same argument that we can deform integration path, and it does not change the value of the integral, because we are integrating a function that is analytic in this domain. So now let us compute the difference of these two Fourier images. It is omega squared plus I epsilon mm, squared, and the numerator is so minus 2 I omega epsilon plus 7 squared. So so we can now say that absolute value of g g epsilon of t minus g of t, which is defined by this integral, is less or equal than um, integral over this circle of a function. No, actually, I shouldn't have closed this. It is just sorry, it is just this. So it less or equal than integral over this integration path of the absolute value of this function. So, well, let us just let us just put absolute value 7 squared minus 2 I 7 omega over omega squared 1 plus I epsilon squared. So we can say that omega is always greater than epsilon, so it is something like well, maybe I can miss something, but anyway, we can write this more carefully, but the idea is the following. Omega is always greater than 1. This is something small. So estimate of this integral is the integral over the integral of 2 epsilon absolute value of omega over omega quarter. Maybe if you put some number like 3 instead of 2, it will be absolutely enough to take into account all these intermediate inequalities. And well, it can be written carefully, of course, but the point is that this integral over this contour is convergent because 1 over omega cube is convergent at infinity, and this integral is of order 1. So it is less or equal than epsilon times some constant, times some constant. So, and this completes the proof. So our original integral over this contour was divergent if you just put a pole on the real line and try to integrate. So it's a hopeless idea. But if you first move this pole outside of the real line and then study the function which we get as a function of this parameter epsilon, we realize that it is a perfectly well-defined analytic function in a sense that we can perform analytic continuation in epsilon precisely in this way. We first integrate contour without changing anything, and then we are free to send epsilon to 0. And this limit is then described by this integral. And this is actually a way to compute analytic continuations of a huge number of functions, because we know that if we deform something and don't cross contours, then function is analytic in this the deformation parameter. And, for example, if we work with some heterogeometric functions or some other integrals, sometimes it is enough just to keep track of the topology of a contour to compute the result of analytic continuation. Like, for example, if you had some function which was given by the integral with this position of poles, like on this poles were here and here, and then we started to compute analytic continuation of this function when this poles move clockwise, like, and they move to this position, and then they swap, like one pole is here, another pole is here. Then we will know that analytic continuation of this original function will be the function will be given by such kind of integral, which can be reduced to sum of the residues plus the same integral. So this is the game which can always be played with this integrals in the complex plane.
So we are just using the principle to draw the functions. We can define the Fourier transform and its inverse by integration on any of these parts, and then if we have four, we just avoid it.
Yes.
And then we find the choice of avoiding it over or under to get 0 for the. Okay, so So it's just the definition of the inverse Fourier transform in this case.
Yes, inverse Fourier transform of the operator, which itself should not have inverse because it has this kernel spanned by exponentials. So it's kind of quasi-inverse. So if apply Green function, then act with the D'Alembert operator, we will get original function. But of course, we could add any such a combination of exponentials, and we still would get the original function. So is it fine? So are there any other questions? Yeah. So, okay, so let us maybe go further. Mm, mm, so, oh, by the way, I forgot to tell one thing about this principal value and all the story. So let us consider the following object. Let us consider an integral from integral in some domain f of x over x plus I epsilon dx. So maybe from minus to plus infinity, it does not matter. So again, we have this situation where this so namely we want to consider the limit epsilon goes to 0 of such integral f over x plus I epsilon. So this pole is under the integration contour, and we can do in the same way. We can move it to the real line and write this integral in this way: x over x plus I epsilon dx, and f of x over x dx over this contour. And now this integral can be split into two parts. So it is, let's call this C0, and this C epsilon. So minus C some nu. From minus nu to nu. So it is a integral over C 0 f of x over x dx plus integral over C nu f of x over x dx. So this first integral can be computed, and it equals to minus pi I f of 0. And the second integral can be, so we see that it is nu independent. So the second integral, since it is nu independent, we can take limit nu goes to 0. So it is plus limit nu goes to 0 integral over c nu f of x over x dx. And we see that it is minus pi I f of 0 plus principal value in this classical sense of f of x over x dx. So if we now compare the left-hand side and the right-hand side, we can say that this expression 1 over x plus I epsilon, its limit when epsilon goes to 0, can be written as a generalized function. Namely, so the result of this consideration is that 1 over, wait, let me check the coordinates. 1. So we conclude that x plus I epsilon limit when epsilon goes to 0 equals to minus pi I delta of x plus principal value of 1 over x. And in the same way, so it is, well, here epsilon is positive. 1 over x minus I epsilon equals to pi I delta of x plus principal value of 1 over x. So having these formulas, it's all also interesting to look what are the what are the epsilon approximations for this generalized function, for delta function, for this one. So we can say that delta epsilon of x equals to what? 1 over 2 pi I, 1 over x minus I epsilon minus 1 over x plus I epsilon. And it equals to what? It equals 1 over pi epsilon over x squared plus epsilon squared. And here we can look at this generalized function as well. So epsilon approximation, it equals to what? It equals to 1/2 1 over x plus I epsilon plus 1 over x minus I epsilon. And it equals to 1 over pi. Oh no, it equals to x over x squared plus epsilon squared. So you can probably remember this function because it was one of the um, epsilon approximation of the delta function, and uh, um, well, we didn't see this function, but its meaning is more or less clear. It is 1 over x in all points different from 0, and it goes to 0 around 0. So uh, so any such integral with a removed region around 0 will converge to so defined principal value. So so there are such nice formulas. So they also have a name. They are called Sokhotsky formulas. Okay, so but very easy to remember because it's the origin of these formulas. So in this computation of residues. So, do you have any questions? So, but yes, let us go back to our gain functions. So, I remove this computation of such integral. So, yeah, actually, the situation is a little bit trickier than for uh, Laplace operator in the sense that different dimensions of the space-time are different. So basically, odd and even dimensions correspond to different behavior of the green function. But let us start computing this dimension by dimension. So let us first compute this green function for d equals to 1. So what do we have? We have this integral. And let us, so g of tx equals to this integral from minus infinity to plus infinity e minus I omega t plus I kx or pi squared. Mm, mm. So here this picture is even more tricky because originally we had only one pole at 0, and here the position of this pole is now plus absolute value of k and minus absolute value of k. So in principle we have different different ways to close this contour. So for our purposes, we of course choose this way. But there is also another choice, which is called, mm, I don't know what is precise name for this contour, but the object is a finite propagator. And this corresponds to, probably I can miss the two contours, but it corresponds to this choice of contour, like in this one. Hmm?
So that integral, we have omega plus I epsilon.
Mm-hmm.
On the start, we should have only omega squared minus k squared, and then,
Yes.
before, if we have a problem in those poles, we do the proof again.
Yes. But we do have problems, so yeah. So, here we choose a contour in this way, but in principle it might happen that correct choice of contour is this one, and it corresponds to the propagator of the form. So this modification is omega squared plus omega squared minus k squared plus I epsilon. And this propagator is actually close friend of a propagator in the propagator for the Laplace operator, because it can be obtained as an analytic continuation from that case. So this object appears in QFT. And it has some different properties other than this green function. For example, this green function has a property that g of x, g of t and x equals to g of minus t minus x. Is symmetric, which is maybe might be wrong. No, it should be fine, because this contour is symmetric under omega to minus omega, k to minus k. So, and it is a correlation function in quantum field theory, which is symmetric under the exchange of variables. But in our case, we are interested in the green function, which corresponds to this nice initial conditions. And
So the epsilon correction is chosen in such a way that corresponds to a choice of avoiding the poles.
yes, so
if I wanted to pass under both of them, I should put omega minus I epsilon.
yes, yes. But we want this. This. So let us compute these residues. So as before, when t is less than 0, it equals to 0. So let us consider only the case when t is greater than 0. In this case, we can close a contour below, and this residue equals to what? So it is minus 2 pi I yeah, it should be. Thanks. So we first compute integral in d omega and keep integral in decay. Over 2 pi. So we have minus 2 pi I times residue of minus e to minus I omega t plus I k x over omega minus k, omega plus k, omega minus k, absolute value of k. This is residue at omega equals to minus absolute value of k. And the second residue is minus 2 pi r residue at omega equals to plus absolute value of k minus e to minus I omega t plus I kx over omega plus absolute value of k omega minus absolute value of k. Okay, so when we compute this residue, and I also missed 1 over 2 pi, minus 2 pi I over 2 pi, minus 2 pi I over 2 pi. So when we compute this residue, we should just remove this term and substitute omega equals to minus absolute value of k everywhere. So it equals to, so to go from minus infinity to plus infinity, decay over 2 pi. No, yes. No, what do you mean? So, yeah. So, so, so this minus sign will cancel from here and from there. So we have overall minus I times e to minus I omega t e to I absolute value of k t plus I kx over 2 absolute value of k minus I times so here instead the substitute here omega equals to absolute value of k, so the denominator has to absolute value of k, and it does not cancel this sign near the exponential, and it is e2 minus I absolute value of k t plus ikx. Well, actually, no one told us that this integral in k is one-dimensional. In principle, we could write here a d-dimensional integral, and here this k would be a vector. But for now, let us restrict to this case. So, so now maybe I can continue here. So minus I is the kind of overall factor. This is minus I integral in decay over 2 pi. And here we have a 2 absolute value of k e to I kx e to I absolute value of kt minus e to I minus I absolute value of kt. Okay, so now, until this part, it will be the same for different dimensions, but in dimension 1, we can notice that this integral from minus infinity to plus infinity can be transformed to integral just from 0 to infinity of difference of these two exponentials, because no, sorry, what am I saying? Sorry.
Is a sine function. Psi of modulus of k times t divided by modulus of k is even.
No, and this one is even, and this one is so let me check. Yeah, this one is even, and this one is not. So we can say that only even part of this uh, no, this not what I wanted.
So just cosine of kx survives.
Mm, no, I'm actually doing something stupid. So look at this function. If k is positive, it equals to e to the plus ikt minus e to the minus ikt divided by 2k. And if k is negative, it is e to the minus ikt minus uh, e to the plus ikt divided by minus 2k. So the point is that it is actually it is actually just this function minus I integral from minus infinity to plus infinity decay over 2 pi e to the I kx to the I kt minus e to the minus ikt over 2k. So do you agree? Because it's a kind of a sign uh, of t absolute value of k over absolute value of k equals to uh, sine of tk over over k. This is this identity for real case. Okay, so now we need to compute this integral in k. So what can I raise? Probably I can raise this computation. So we are computing this minus I integral from minus infinity to plus infinity decay over 2 pi. So let us write like this, and there is e to the k kx e to the ikt minus e to the minus ikt over 2k. So we see that this function is regular at 0. And since it's regular, we can rewrite this integral as an integral over such contour. So it's innocent procedure. And we call this contour C+. And once we do this, we can now separate this integral into two parts, because in principle each of these parts has a pole at 0, and this integral is not well defined. But if we define this contour, then each of them becomes well defined. So we can say that it is minus I integral over C plus of decay over 2 pi ikx plus t over 2k plus I integral over C plus decay over 2 pi e to the my ik x minus t over 2k. And now again we have integral over C plus, and if coefficient in front of, so if a coefficient in front of k is positive, we can close this contour in the upper half plane, and the integral will equal to 0. So we can immediately write that this first integral is proportional to Heaviside theta of minus x minus t. And then we will compute the next part. And this integral is proportional to Heaviside theta of t minus x, so on. Is it clear? So when x plus t is positive, this integral can be closed in the upper in the upper half plane. But actually, no. Maybe it was not the best choice of contour, but in any way. And now let us compute the residue. So it's residue at 0. So it is minus minus pi I, since we integrate in the clockwise direction, times minus I. So it is minus pi over 2 pi. And here in the same way we get pi over 2 pi. So we get the sine theta of actually I don't like this in this representation. So let us draw this function for some positive value of t. So when x is negative, so it is this gain function of x, and this is x, tx. So when x is big negative, then both heaviside thetas are of a negative argument, so it is 0. Then when x equals to minus t, this so which one? This heaviside theta becomes positive. Actually, probably I missed the signs. Maybe it's fine. Okay, probably I missed some sign, but I'm not sure. So this heaviside theta becomes no, I was wrong. When x is big negative, then both thetas equal to 1. When x equals to minus t, one of them vanishes, this one, and another one equals to 1. So here we get 1/2. And this is my minus t. And when x becomes equal to plus t, then both of these heaviside thetas vanish again. So here the part of this gain function, so it can be now rewritten as a heaviside theta of absolute value of x minus absolute value of t, like this, 1/2. And we should also remember that it vanishes for negative t. So so we should also multiply it by theta of t. No, sorry. Absolute value of t minus x. So if you try to plot this, then it has the following form. It equals to 1 in this domain, or to 1/2. Yes, times heaviside theta of t, because it was from the very beginning. This integral vanishes when time is negative. So here is the answer for the gain function in one dimension, in 1 plus 1. Okay, so are there any questions about this? So yes, sorry, I did not update anything. I will do it probably, well, today, and I'll write you an email. Okay. So. Yeah. Thanks for your attention. Bye.